Hello students, this is second lecture on quotient group. In the previous lecture, we have defined quotient group and then proved some theorem on quotient group. In this lecture, we will prove some more theorems and solve problem based on the quotient group. Let's prove the theorem. Prove that every quotient group of a cyclic group is cyclic. Prove that every quotient group of a cyclic group is cyclic. Proof is what is given. Let G be a cyclic group generated by A. So generator fails. Therefore, generator fails. G is A. And we also know that every cyclic group is abelian. Therefore, G is an abelian group. Every subgroup of an abelian group is normal. So G is abelian. Therefore, every subgroup of G is normal. So let H is a subgroup of G. Let is a subgroup of G. Therefore, H is a normal subgroup of G. Thus, G upon H is a quotient group. Thus, G upon H is a quotient group. Now, our aim is to show that G upon H is this quotient group is a cyclic group generated by HA. Our aim to show that this quotient group G upon H, set of all right cosets of H in G, set of all right cosets H in G is a cyclic group generated by HA. So for that, let us take Hx belongs to this quotient group G oblique H, any element of this. That is X belongs to this quotient group in G upon H, any element of any element of this or arbitrary element for all X belongs to G. But G is a cyclic group generated by A. Therefore, X also belongs to G. So, therefore, X will be of the type X is equal to A square N for some N belongs to X belongs to A generator of this, A generator of G, and X belongs to G. So X will be in the powers of A. Therefore, Hx is equal to substitute value of A, H of A square N, H of A square N is equal to H of A into A into A to N times is equal to now the definition of quotient group is equal to under binary multiplication is equal to HA into HA into HA into HA N times is equal to HA raised to power N. H into HA to H raised to power N. So H of X comes out to be H of A raised to power N for all HA belongs to the quotient group G upon H. Therefore, G upon is a cyclic group generated by HA. Hence, each quotient group of a cyclic group is cyclic. Each quotient group of a cyclic group is cyclic group. The converse of the above theorem is not true. That is, the quotient group may be a cyclic group without being the group cyclic. Quotient group may be a cyclic group without being the group is cyclic. Next one is let G be a group such that G upon ZG is cyclic. G is a group such that G upon ZG is a cyclic where ZG is the center of the group G. Then G is empty. Then we show that G is empty. Let us take H is equal to ZG. Then this quotient group G upon ZG can be G upon H, which is given to be is a cyclic um, group generated by H. Group generated by H. Let A and B be any elements of G. Let A and B belong to be any elements of G and two elements of G. Then HA and HB belongs to the this quotient group H upon G, which is a cyclic group generated by HA. Therefore, HA will be of the type HA will be HG is for N because HG is a cyclic group generated by HG. So the elements of HG will be in the powers of HG. So this implies H is equal to H is equal to H0 to N and HB is equal to H equal M. H is equal to M for some and integers. For some integer M. Now Hg is written as, how we can write this Hg? H is equal to H, A is equal to Hg, equal to Hg, to Hg. How many power? This power is n. This n time. So if we repeatedly apply the definition quotient rule, this is equal to H in G, Hg, Hg is equal to H G square, Hg square into Hg is equal to Hg is equal to 3 and so on up to this become Hg is power n. Similarly, Hb is equal to Hg into Hg into Hg repeated m times is equal to become by the repeat application because this is quotient. So this is equal to Hg is power brought to the calculations. Now, because H is equal to GH, H A is equal to HB implies AB was belongs to AB was belongs to H. Using this here from the right side. So now HA is equal to HG is per N. HG is equal to HG per N. This implies HG using this H is per minus N belongs to H. Similarly, HB is equal to H is per M implies HB G is per minus M belongs to H. This implies A G is per minus N. If this belongs to H, this will be equal to X, and this will be equal to X, and B G inverse is equal to Y for some X belongs to H. If they belongs to H, we have taken two elements X belongs to this. So then A can be written as X G is power N cancellation law, right? Cancellation law. A can be written as G X G is power M and B is written as Y G is power M. A belongs to G. Now we are given that G is an we have to show G is abelian. G is abelian. So let's show that we have to show AB is equal to A belongs to G, AB is equal to BA. AB is equal to, so G is abelian. So AB is equal to substitute the value of A and B. So this A X G is per M, Y G is per M is equal to X. Now Y belongs to H, Y belongs to the center of group, Y to center of group. And the definition of the center of group. So this is equal to G inverse Y is equal to Y G inverse. H means and X G belongs to G, therefore Y is equal to this equal to X Y G inverse Y is equal to G Y G inverse X Y associative law holds true. X Y G is to M, G is power N, G power M. So this is equal to X Y G is power N plus M. Similarly, B A is equal to Y G is power M, X G is power N is equal to Y associative law G is power M, X is equal to X, X G is power M is equal to N. X belongs to X because X belongs to the central. So this is written as X Y Y X G is power M G power N is equal to Y X Y X G is power M plus N, M and N integers, therefore Y X is power M plus N. So X Y first second implies AB is equal to BA is true as if implies AB is equal to BA implies XY is equal to YX. XY is equal to YX. X and Y belongs to the H. So XY belongs to they both belongs to the XY belongs to G. H means XY is equal to YX holds in the center group. So this is equal to this implies G is the attribute as XY is equal to YX because both belong to the center group. So implies G is the attribute. Now next theorem is let H be a normal subgroup of group G. Show that G upon H quotient group is an abelian. If and only if X Y X inverse Y inverse belongs to H for all X belongs to G. If H is a normal subgroup of G, normal subgroup G, then show that G upon is abelian. If this holds, Again, if and only if x, y, x inverse, y inverse belongs to H for all x. The necessary part is, let us suppose that given is H normal subgroup G such that this is empty. Our aim is to show that our aim is to prove that x, y inverse, x inverse, y inverse belongs to H for all x. That is, I want to show that h of xy, h of xy, x inverse y inverse is equal to h. Now, take the left hand side. H of xy, x inverse y inverse is equal to h is a normal subgroup of G. H is a normal subgroup of G. So this is equal to, because it is this is equal to h of x, h of y, h inverse x, h inverse y. So uh, h inverse x inverse is equal to h x inverse. We have proved this. Hx is equal to hx whole inverse. Hy inverse is equal to h whole inverse is equal to, so x hx hy x inverse can be written as x hx inverse hy inverse is written as hy inverse. So now h to the wholes, G is the quotient group, Laplacian group. So therefore hx hy hx hy the commutes. So this is equal to hy hx inverse can be written as hx inverse and hy inverse. So hx inverse is equal to h. This will be h into, this will become h into hx is equal to h, or this will become h into h of hx x inverse hy of y inverse is equal to h into h and h. So this implies h into h is equal to h. Yeah. This implies h of xy x inverse y inverse is equal to h, implies xy x inverse y inverse to h for xy. So now sufficient part is, let for all x belongs to G, hx sorry xy x inverse y inverse belongs to h. Our aim is to prove that this quotient group G upon h is an ability, where h is a normal subgroup. Since we are given that xy x inverse y inverse belongs to h, implies, what does it imply? It implies if this belongs to this, we have proved the difference result. H of xy x inverse y inverse to h. Now h of xy x inverse y is going to be written as h of x, h of y, h of x inverse, h of y inverse, h of x inverse, h of x inverse, h of y inverse, h inverse, h inverse. So h of x inverse is equal to h of x whole inverse, h of y inverse is equal to h of y whole inverse. Now cancellation law, we can apply cancellation law here. Write cancellation by h y inverse, h y. H inverse to h y inverse into h is equal to h. H inverse into h is equal to hx into hx equal to hx. This is equal to this become h into e, or it's into h. H into this will be hy. And similarly, let us consider by hx in hx. Hx y hx hy is equal to hy hx. Then let us hx into hx. H x into h x inverse is equal to identity element h e, h into h, h into h is equal to h again, h into h is equal to h e into h y is equal to h of y, h of y the whole group. So this implies g is nothing, h x is h y is equal to h y x. This question could be that. Now let's solve for this one. Let G be a group of all non-singular upper triangular matrices towards second order matrices over reals. That is, G consists of A, B, 0, D. A, B, D are reals, and there A, D is not equal to 0. And it's not equal to 0. Show that H consisting of 1, B, 0, 1, B is a real number, is a normal subgroup of G, and G upon H is an abelian subgroup of G, where G is not an abelian. Solution is given. G is the G is the set of all non-singular matrices of second order of the type A, B, 0, D, A, B, D are real numbers, and A, D is not equal to 0. The intermediate is not equal to 0. And H consists of 1, B, 0, 1. B is a real number, and determinant is not equal to 0. Determinant is equal to 1. Now, on comparing this, we come to know that H is subgroup of G. It is a subset of G. So essentially, H is a subgroup of G. H is a subgroup of G. Uh, Now we have to show that H is subgroup of G. Now we will show that H is subgroup. So let's take two elements from H. Let's take two elements A and B from H. Then A will type 1C01, B is type 1D01. You can take any element. They have the number A, B, and C, and D. So A to B is equal to, when you multiply 1C01, 1D01, we will get 1 C plus D 01 belongs to, is a real number, not to H. Similarly, if A belongs to A is equal to A C01 and determinant of A is equal to 1, then it's equal to 1, so adjoint this is not equal to 0, so you can find the inverse of A. The inverse is equal to adjoint of A determinant. Adjoint of A is the element value cofactor, and translate to that upon determinant of A. Determinant is equal to 1, so this is equal to, this comes out to be 1 minus C01 belongs to H. So for all A belongs to H, this lemma, you put that A belongs to H, those property holds and inverse element exists. Implies this H is a subgroup. Yeah. Now we will show that H is a normal subgroup. So normal subgroup. Let's take X belongs to G and A belongs to H. We have shown this is minority. First, this is a subset. This is minority. It's given. So subset, minority subset, subgroup. Now a minority is a normal subgroup. So let us take X belongs to G and A belongs to H. So if X belongs to G, you type A, B, 0, D. A B are real numbers and A D is not equal to 0. And determinant of this implies determinant of X is not equal to 0. So we can find inverse of X. This is adjoint of A upon determinant of A. So determinant of A comes out to AD, and this is equal to A, D, and this is adjoint of A. If this is element cofactor, then transfer this. And this comes out to be inverse comes out to this. So A is this, A is 1, C is 0, 1 for some 0. So now we find the product A X inverse multiply this and this plus this multiply A this X with this the resultant, we got X is equal to this much, and subsequently we got 1 is a real number, real but this is a real number 0 1. This belongs to H. It's agreement with any real number belongs to H, implies for all A belongs to H, X belongs to G, X inverse belongs to H, implies H is a normal subgroup of G. So therefore, G upon H is a quotient group. Fourth is show that this is a abelian. Now to show that G upon H is an abelian group. So let Hx and Hy belong to this quotient group. There are two right quotients of this set of right quotients quotient group for all H. Then G upon H is abelian if and only if Hx Hy is equal to Hy Hx. So H of definition of the quotient group Hxy Hx Hy is equal to H of Xy. H of Y H of X H of Yx. So H of Xy is equal to H of Yx implies if and only if Xy Xy Y inverse X belongs to H. So Xy Y inverse X inverse of Yx is equal to X inverse Y inverse. This implies Xy X inverse Y inverse belongs to H. So now let's take Xy belongs to G. X is a matrix, Y is matrix is. Now X inverse is this, X inverse is this, Y inverse is this, Y inverse, adjoint to inverse is determinant of it. So xy into x inverse y inverse is equal to xy. This is x into y. This is x inverse y inverse. This comes out to this, and their product. When we multiplied them, we got 110, and this is a real number. We belong to h. Implies xy x inverse belongs to h. This is abelian group. But G is a little bit because matrix multiplication is not always commutative. Thank you very much.